Okay, so good morning. So let me start. So let me recap. So today I will introduce a second model for disordered system, but let me recap what we did yesterday. So I will write here, I'll write it here. This is a recap. So yesterday we introduced a model which is called REM, okay? Where we have energy, so we said we have a set of random numbers, E1, E2, EM. And they are random numbers, okay, taken from a Gaussian distribution of zero mean and n variance, and there is a relation, we said m is equal to 2 power n, okay? And so this means that the energy is a random number of the order square root of n, and I have a huge number of data points. And then we first solved the thermodynamics of this model, and we show that we can write, let's say, the free energy with an intensive part times n. This is for large n because it's self-averaging. Okay. And then we were able to find this intensive variable. Okay, there is a phase transition. So I forget the minus in the lecture, but I gave you in the tutorial. So there is log of 2 beta plus beta over 2 at high temperature. And then we have a freezing transition when I'm at a low temperature. And we show that beta C is equal to this value. Okay, this was one result. And then the second result was the scaling of the minimum. So when beta goes to infinity, the free energy becomes the minimal energy. So here I prefer to use the extensive minimum, so the times n. And so what we show is that the minimum is actually deterministic. So it's fluctuating, but there is the dominant part is deterministic. And so we have this 2 log 2 n, which is exactly this one, okay? And we are happy because it's extensive, and the prefactor is the one which was found with the first method. But then for this minimum, we are able also to find the correction. And so there is a first deterministic correction, which is a complicated number, log 4 pi log 2 divided square root of 2 log 2. And there is a log n, the most important part. So it's subdominant, but still deterministic. And then we have a part which is fluctuating. This number chi is a number of order 1, and I showed yesterday that it was Gumbel distributed, okay? And the fluctuations are of the order square root 2 log 2, so are of the order 1, okay? We said this is very important. We will see that this will characterize the glassy phase, okay? So essentially, these are the two results we had yesterday. And today, I want to introduce a different model, which is called the directed polymer in random media. Okay. So this model is a model that, depending the dimension, it will show something which is very similar to this one, but a low dimension will show a different physics, a different glassy physics. And I want to show this as the two, let's say, extreme of what can happen in the thermodynamic properties of a disordered system. So let me define the model first on the lattice. And let me say that this model, I love it because is a model that you can solve numerically very well, which is something very difficult in disordered system because of what I told you yesterday, that in general, you have a huge number of configuration, but to find the minimum is very difficult because there is frustration, okay? And for this model, actually, you have an algorithm that allows you to find the minimum in a very efficient way. And this will be the tutorial of today. It will be done by Ivan. And it will be, so if you have a computer, it will be great. You can use Google Colab, you can use Python, and you can actually understand this algorithm. And the idea is that this algorithm is the same algorithm that you use when you, in Google Map, you find your itinerary. Dijkstra algorithm is the algorithm that you use in order to optimize your path. And what I will show today is this polymer is a path. So let me draw the model on the discrete. And then in the second part, we will start the continuum version of the model. Okay? So here I do things like this. This is the difficult part. So let me do this, like this. So I'm not. So here you have what you call the time. Let's call it. Let me call it like this. Let me do. This is x, the position, and this is tau, the time. And let's say that we are going from the time tau equal to 0 to the time tau equal to t. And this lattice is so strange because we want to make the model as simple as possible. And so one configuration in this model, so let me erase what is not necessary. Okay. A configuration in this model is just a directed path. So every time you have to go up. So every time you have two choices, either you go right, either you go left. Let's say that this time I go right, second time I go right, then left, left, then right. So this is a configuration. I hope you see there. So let me say x of tau is a path. And this direct, so we call this time because unfortunately you cannot ever go back in time. You're always forced to go up. And so every time you are forced to go up. So we want to avoid things like this. You cannot do paths of this kind, which are non-directed, okay? So directed means every time you start from 0, 0, okay? This is the position 0, 0. You end up at the position x, t, okay? And so how many paths do you have if you want to arrive up to the level t? Every time you have two choices, either you go left, either you go right. So if t equal to 1, you have two possibilities. If t equal to 2, you have 4 possibilities. So in general, you have m equal to power t possibility, okay? So here it was 2 power n, so n was the number of spins. Here 2 power t, t is the length of your polymer, okay? And now let's say, so this is the part directed polymer. Now we have to put the randomness, okay? And now the randomness is at each side. So you take a position x tau. So let's say you have a random number v x tau tau. And as usual, for simplicity, we take a Gaussian number in 0, 1, okay? I don't know how. So v x tau tau is a Gaussian number of mean 0 and variance 1, exactly like yesterday, Jij was 0, 1, okay? And now let's define the energy E associated to a path in a simple way. It's just the sum of tau going through 1, or from 0, let's say, to t of v x tau tau. So you v is the potential, let's say, and is a random number. So is sitting on each one of these sides of your lattice, okay? So you have your path orange, and you are summing the v that you have along the path. If you want, is the price that you have to pay in order to go to this particular site, okay? Or what you gain if the v is negative, okay? And so what you would like to do in thermodynamics, so if you now are at the temperature, inverse temperature beta, or at temperature capital T, as you prefer, what you would like is to okay, you can define the partition function of this model Z, okay? So now we have to define a little bit what we want to do. So you have to decide what are the paths you are considering, okay? You can consider the paths always start in 0, 0, but they can end in xt, or they can end whatever they want. So if I write like this, it means that I consider only the path that end in xt. Then we will count how many they are, okay? But so now what you will do is that you sum all the paths x tau that goes from 0, 0 to xt, okay? And then you will have exponential minus beta, the energy of this path, which is exponential minus beta sum v x tau tau, and then tau from 0 to t, and then you have to impose the boundary on the path. So you understand what we are doing. So you take, for example, an ending point. You can also decide that you want to sum over all path. This is another possibility. You select all the path with this feature. There are many, okay? If you take all the path, they are 2 power t. And then, but they have a different weight, and this is the weight, the Boltzmann weight associated to each path, okay? And so the path that have a smaller energy, maybe a path with a negative energy, will have a much bigger weight than the path with a positive energy, okay? And again, as yesterday, today, I mean, this afternoon, when each one of you will have its own directed polymer, its own computer, the energies associated to a given path will be different because these random numbers are different. So each one, it will have its own sample. And the question is the ground state energy again, deterministic, and do we have a phase transition, and so on. So what are the questions we would like to answer for this problem? So let me first say another thing about the model. So this model that I just defined, new, is in a dimension D, which is equal to 1 plus 1. So this is the way we indicate the problem. Why? Because we have a line, a path, which has a dimension 1, and is moving in a two dimensions. So we say 1 is the external dimension, okay? In general, you can say that polymers, directed polymers, can be like this, can be a path, for example, in 3 dimensions, okay? So if you have D equal 1 plus 2, it means that you have a line that grows in 2 dimensions. For example, a vortex of a superconductor in 3 dimensions, or vortices, is a line with n equal to 2, okay? And in general, the model is D equal 1 plus n. This is a polymer that moves in a dimension embedded space, which is n dimension, okay? So the embedded space is 1 plus n, but okay, the n is the dimension of x, and is the dimension of x, and 1 is the dimension, the internal dimension. So we always want a polymer. So in order to have a polymer, it should be 1, the internal dimension of my interface, okay? So this problem is a problem that has been studied for different value of n, and we will see that depending on the value of n, there will be the difference between the new physics and a physics which is similar for REM. I can already tell you that when n goes to infinity, you find the REM physics, because again, you see that this energy is the sum of T Gaussian numbers. So it will be a number which is Gaussian with the variance equal to T. And so in some sense, if you forget the interaction, you expect to have the physics of the REM. And actually this occurs when n is very large. But today we will be more interested in the opposite case, which is n equal to 1, which is what I define here. So it's really the opposite of the REM, and we will find a different physics. Okay, it's clear the model, how it is defined. Okay, so let's see some property. So there is, okay. Let's see some properties of this model. So let me focus first on this one-dimensional model. And what? It's also random. Yes. So you fix a trajectory. So let's fix the trajectory which is here. So each one of you look the energy associated to this trajectory, but because each one of you have a different realization of the disorder, will tell me a different number, which is a Gaussian number with 0 mean and 1, 2, 3, 4, 5, 6, 7, and variance equal to 7, okay? So each one for a given trajectory will tell me exactly the same thing. So what we would like is the following thing. The first question is, if we want to know if there is a phase transition of n, where n now is this dimension of the polymer. So here we are looking n equal to 1, okay? So n is not the number of spin. Today, n is the external, is the dimension of the vector x. The second question we would like to answer is if there is a glass phase for n equal 1, 2, etc. And then we would like to know what are the properties of the minimum, okay? So it will be, again, self-averaging and extensive, okay? But E mean of T, okay? What we would like to know is the typical value, which should be deterministic, the fluctuations, okay? And then the difference with the REM, in the REM, the configuration was IID, so there was no connection between the energy configuration, while here we have a real model, microscopic model. So could we say something about the shape of the polymers at low energy? Okay, so let's say that you look, for example, the ground state. What is the shape? Is a random object, but as a shape which is particularly interesting or not. So, okay, so let me ask you the following question. So, for example, let's say that we are at infinite temperature, and now if we are at infinite temperature, so then we can essentially take V equal to 0. So if we don't have any disorder, because all the configuration has the same weight, then we pick at random one polymer. Okay, so let's say with the you don't fix, so you start from 0, 0. Now the question is which value of x you pick at the time t, okay? Okay, so you pick at random, so you have 2 power t polymers. Let's say that I pick the number 37. So what is the shape of this polymer? So what you are doing is you are doing a random walk. Every time you go left with probability 1/2, right with probability 1/2, and you do t steps, okay? So let's say that I want to determine, so this will be, so what is this probability of having certain value x is the number of paths that ends up in x divided 2 power t, which is the total number of paths, no? So now, what is the number of polymers that start in 0, 0 and ends up in 0t? So you do this, the same number of plus as the same number of minus, or the same number of right and the same number of left. So how many possibilities I have to find this number, to find this configuration? What potential? Okay, the potential is given, is always this one, okay? So now what I'm saying in infinite temperature, all the paths have the same weight, okay? which is the same thing, is to say, if I look at the pure problem without the potential, then all the path has the same energy, 0, and so I pick one of them at random. Okay, so it's a kind of infinite limit calculation. Okay, infinite temperature calculation. Okay, so here, if you want, all paths have the same probability. Okay, so if you imagine that all paths have the same probability, if ending in 0, 0 has much more path that ending in minus t, then most of the time you will be in 0, 0 and not in minus t. So now what we are saying is, let's count how many paths, so let's count how many paths you have starting from 0 and ending up in 0. So this is a calculation t factorial divided t by 2 factorial, t by 2 factorial. This is the number of paths, all the paths, which are many, they start in 0 and ends up in 0, and this is the binomial coefficient t by 2. Okay? And so this at the dominant order is very similar. If you use the Stirling formula, is very similar to 2 power t. Okay? So most of the path, a big fraction of the path, ends up in the origin, while you have only one path that ends up here. Okay? At the border of the, so here you have to do -1, -1, -1, -1. It's very unlikely. So if I say, I have a polymath random and I select this one, you will say that I've cheated because it's very unlikely that I select in the millions and millions of paths that one. Most of the path ends up in the origin, okay? And now if you want to say what is the number of polymers that start at 0, 0 and ends up in xt, then you have to use a different binomial coefficient. So it will be t minus 6 over 2 will be minus, t plus x over 2 will be plus. So this is the number of them. This is the number of paths that ends up in x, okay? And then in order to have an idea, we can define an entropy, capital S, of ending in x at time t, okay? And this will be the log of this number. So I will not do the calculation, but you have a formula that tells you that the log of t factorial is t log t log t minus t, I think. No, this is the Stirling formula. So if you use the Stirling formula, what you have is that here you have t log 2. So this is the term which is 2 power t, is the dominant term of and then you have a suppression due to x, which is x squared over 2t, and then you have correction, okay? So this means that if you are in the middle, you have the maximal probability, okay? And because this is an entropy and the number is exponential of this thing, it will mean that the probability to be in x t, it is close to the origin exponential minus x squared over 2t divided, in order to have a probability, 2 pi t. Okay? So this is not very strange. You have a random walk, okay? You compute the variance of these jumps +1 and -1, and this gives you the fact that at large t, you recover the results that you know for the Brownian motion and the distribution of the ending. So you are doing a random walk. So you say where I am at time t, but you will be a Gaussian distribution because you start from 0. You have a Gaussian distribution, and x square of t, it will be t, no? I think. So you have an excursion which is square root of t. So essentially, most of you will find that if you pick at random a polymer, your excursion is of the order square root of t. So which means that the shape of the polymer, which is typical, is a polymer that is executing a random walk, and the final position is of the order square root of t, is a random number with a Gaussian distribution of the order of square root of t. Okay? This is not the optimized one. So it's the one without taking an account the optimization. Okay? So if we answer to the question, what is the shape of the polymer at infinite energy, okay, in the typical polymer, they have it's called usually in the language of the polymer, the roughness exponent. So you say that x of t goes with t power zeta, okay, with some prefactor kappa 2, and chi, which is a random number of order 1, okay, let me call it chi tilde, it has a different, is not Gumbel distributed. So the scaling in t, so let me say what I mean with this. When I write things like this, I mean the following thing. I mean, the model, I define the model with Gaussian random number with this particular lattice, okay? And this will enter in this value kappa 2, which is a non-universal number. Then I have a scaling that comes from diffusion, which is square root of t that I expect no matter which random walk. And then chi, it is a distribution which is universal, and for diffusion is the Gaussian distribution. Okay, so for the infinite temperature is a problem which is very simple. I expect to have some Gaussian with some exponent zeta, which is 1/2, because this is the diffusion. So what you will see with Ivan is that if you now ask what is the best energy, then you are ready to pay an entropic cost, so to go in region where there are less polymer in order to pick the V which are negative. So the zeta that you measure at finite temperature or at 0 temperature is actually different, and is 2/3 is bigger, okay, is more rough, the polymer in the ground state. So now you're asking, I want to solve not to pick a polymer at random. I give the random number, and it will show you how to find the ground state energy in this lattice, okay? And when you see this ground state energy, if you measure the roughness of the polymer, it will not be 1/2, it will be 2/3. This I'm not showing now, it will show you numerically, okay? Is a result that is known exactly, and it has a consequence in the ground state energy. So this is the zeta that you measure when n is equal to 1, okay? And if you want to know what is the shape of E mean, it is a random number. of this form, there is an exponent theta, kappa 2, and then there is a second, I don't know how to call it, E2, I don't know, random variable, okay? So this is the deterministic part, okay? This is what we found also yesterday. So in the REM model, it was -2 log 2 times n, where n was the size of the system. Here, the size of the system is t, and still we have a deterministic part. So each one of you will find a ground state energy which is very similar, okay, because the only difference is here. So they have fluctuation, but this is the deterministic part. Which is extensive, okay? And then this part is the fluctuation, are the fluctuations. And at variance with the REM, where the fluctuations were of the order 1, so there was no n dependence here. Here there is the dependence on the size of the system, and actually you can measure that theta is equal to 1/3 in n equal to 1, okay? So if you have a polymer in 2 dimensions, so the polymer, the external dimension is 1, then you have 2 exponents which are well known, is 2/3 for the roughness, 1/3 for the fluctuation of the ground state. And these exponents actually are in a universality class which is called Kardar-Parisi-Zhang, okay? Because the directed polymer in random media, I mean, if you take the free energy, you can map it on the Kardar-Parisi-Zhang equation. And so the 2 exponents are known since a long time. Actually, I think that Abhishek Dhar was the first to show in a model this exponent 1/3, but then it was not related to the other models. And then in the paper of Kardar, Parisi, and Zhang, there was the relation between the directed polymer, the Kardar-Parisi-Zhang equation, and these exponents are given as the exponents of the roughness of the polymer and of the fluctuation of the free energy and the ground state energy. So this is a model in which the ground state energy fluctuates much more than in the REM with an exponent theta which is positive. And all the time you have this exponent theta which is positive, it will be a different physics. Now theta and zeta depends on n, and in particular when n goes to infinity, theta become equal to 0, and this is the reason why you find back the physics of the random energy model. And so now what I will do is the following things, is the, maybe I want to say another point, because I don't know what are your interests. So let's say that I said that in the Kardar-Parisi-Zhang equation, people at the end of the 80s understood that these were the exponents for the model D equal 1 plus 1, okay, n equal to 1. Okay, 1/3 and 2/3. But then around 2000, there was a new discovery, which was, then it was a big discovery, that actually this chi2 is a random number, but now we know what is the distribution of this random number. As I said, in the REM, it's very simple, it's the Gumbel distribution. I could do it in the tutorial. This distribution of chi2 is much more difficult to understand what it is, and actually is the Tracy-Widom distribution, which is the distribution of the smallest eigenvalues of a random matrix, Gaussian random matrix. And now setting the boundary condition, for example, if you set the polymer starting 0 and arriving 0, this is what is called the droplet boundary condition, then is the Tracy-Widom F2, which corresponds to Gaussian Hermitian matrix. So if you take a random matrix, which is Gaussian and Hermitian, you compute the eigenvalue, you pick the smallest one, and then you redo this 1,000th of time, you do make the distribution, and you will find this is exactly the same as the distribution of the ground state energy of the directed polymer in 1+1 dimension. We don't know what happens in 1+2 dimension and so on. So we can solve this problem completely only in 1+1 dimension. Okay, to do that, you need to use at least the Bethe-Ansatz solution, so it's not easy, but is a problem that attracts a lot of interest because it's integrable in 1+1 dimension. So this is all I want to say in general to this class of model. So now what we will do are two things. With Ivan, you will study how to deal with this model numerically and to found the ground state. There are not a lot of models in disordered system where you can find the ground state exactly in short time. Usually you have to enumerate the 2 power t configuration and pick the smallest one, or you can do Monte Carlo with a lot of massage, annealing, and so on in order to hope that you are taking the low energy states. For the directed polymer, and only for him, you can, or for it, you can actually pick the ground state very easily. There is also the 2-dimensional spin glass system with a more difficult algorithm, but there are really, you count in one hand what are the model where you can do the optimization. So this will be one way. And the second way is to look at the continuum model, which is the one you can integrate and show, for example, the Tracy Widom and so on. We will not do all of that. We will look at this model in dimension 1 today and tomorrow in dimension n, and we will see that just looking at the first moments of the partition function, we can already see when there is a glassy phase. To answer to these two questions, there is a phase transition, and if there is a glassy phase, okay? And then we will argue what is the difference between the different glassy phases, REM and directed polymer, okay? It's clear the model discrete. Okay, I can remove it. No, it's positive, I can tell you. It's non-numerically very, so there are a lot of numerical simulation thanks to this algorithm. I can tell you that is positive, and there is a value, but which is below 1/3. But yes, there is no analytical solution, no exact solution for that. Okay. So now what we want to do is to transform our path x of tau, which was a random walk +1 - 1, okay, in a path which is continuum in time and space. So in the free case, when v equal to 0, we want to say that the path, let's say zeta xt, it will be the integral between all possible paths that start from 0 and end up in x. This is t. Okay. And then we want to sum all of them. And now when you are in continuum, to say sum over all path, you put this integral. So this integral means sum of all paths, and I want this condition. Okay. And now we have exponential minus beta. Okay. And then let me say that minus beta is 1/t. Let me introduce capital T. This is the temperature, and now we want to use the probability distribution of having a trajectory x of t, okay? This I will not show, but is essentially this one, okay? So this is a given, so you take a trajectory, and this will be the trajectory is actually the stationary solution of the Fokker-Planck equation for the simple diffusion, and is what gives you the fact that, so let me put 1/2 here, because I like this, and so is what gives you that x of t squared is equal to capital T of t. Okay, is what gives you diffusion. So is a kind of continuum limit of a random walk, and this is the probability to have a given trajectory x of t, x of tau. And so when I use these brackets like this, I mean the average over all the free trajectories. So this means the average over the free trajectories which means v equal to 0, okay? So really the Brownian trajectories, okay? So, and so now if we want to do the case v different from 0, what we have to do is to add a potential here, okay? So this is, if you want, the elastic term of the polymer. And this is the disordered term. Okay. And you have a competition between the elasticity that would like to have the polymer flat. So to minimize this term, you want the x of t doesn't fluctuate, and this one, which is the disorder, which is fluctuating. And now we want to say that the average of the disorder I will indicate with the brackets, no, with the over bar, sorry. In average is 0, and we take a Gaussian disorder this we will use tomorrow, okay? That is, I think is d delta x minus x prime delta t minus 2. I will not really use today, but we will use it tomorrow. But I will use this disorder, okay, which is, again, the important thing is that you see this is a quadratic term. This is strongly non-quadratic because it's stochastic, non-linear. It has everything terrible that you can imagine. Okay, and so what we want to do, our goal is to determine what is this. This is a random object, and we want to average this over the disorder and to look at the first moments to see if it's glassy or not. Remember, the condition was if z squared x of t divided z x of t square is equal to 1, then z of xt is self-averaging. Otherwise, the other thing that can happen, that was happening to the ramp, is that when this quantity fluctuates hugely, then you are in the glassy phase, and the quenched log of z is smaller than log of z, like this. So the quenched average and the annealed average, they become different. Here they are equal, okay? So we are able to use, to study this model and to show when this occurs, okay? But this, so today I will do some step, and then we will end up tomorrow. Let me check what time is it. Here I have the European time. 40 minutes, okay, it's okay. Okay, to do that, so if you look at this model, if you are a pro in quantum mechanics, you will see that if you take the time imaginary, if you take t equal h bar, small t equal I, small tau, sorry, equal I t prime, and so on, then you recognize that this is the path integral representation of a quantum particle with a time-dependent potential. So if v equal to 0 is the free quantum particle, if v is different from 0, time-independent is a quantum particle in a potential. This is particularly challenging because there is the time also in the potential, okay? You have to do the things, you will have a minus that come out from here, so here we remain a minus, but okay, there is this connection. If you're not a pro in quantum mechanics, there is no problem, I will do everything from scratch, but there is a method that is called Feynman-Katz formula that allows you to go from this path integral object, which is the sum over all path, to a differential equation for z, which is called Schrödinger differential equation, okay? So we want to find the Schrödinger differential equation of this path integral formulation of the partition function. So in quantum mechanics, z is the propagator, okay? But okay, no matter. So what we do is that we want to, essentially, we want to work with the average over the free path. So we don't want to work with an action, with this term, the exponential that is an action in quantum mechanics. We don't want to work with V. So to remove V in a kind of simple way, what we do is that we introduce a new quantity that I call AXT, which is the path integral over the free path x of t equal x and x of 0 equals 0. So here I have just the first part, minus 1 over t integral 0 to t d tau x square. And here I put a delta function a minus the integral 0 to t d tau vx tau tau. Okay? So essentially what I mean is that I would like to make the average over all paths that has this, they are free over these things. But to make the connection more clear, the second thing I will do is I will introduce the Laplace transform. So I will introduce equal zp xt. I will do this moment generating function of p a xt. And this is something more similar to what I want to do, is the integral z x tau x 0 x t equal to x. Then I have the weight of the path, which are this one. Okay. Times okay. So this means that now I'm summing only over the free path, and this became unobservable, okay? It's not anymore part of the weight, the weight is here, and this is the observable I want to measure. Okay, and now using this trick, I can actually write ZP x at time t plus delta t. So what I'm doing is I want to know what is Z for path the starting 0 ends up in x, but not at the time t, at the time t plus delta t. Could I express this as a function of what happened up to the time t? And so this is, so I use this symbol. So for this part, I use this symbol. So I have exponential minus p integral from 0 to t plus dt of d tau v x tau tau. So now this average means this integral, but now here there is t plus dt, but with this weight, okay? So with the weight of the Brownian motion. And so this can be written as two parts. I have the exponential minus p integral from 0 to t d tau v x tau tau times the last piece, which is between t and t plus dt, okay? So I have exponential minus the integral from t plus dt d tau, and now d tau, yes. And now I have ev, but at the end I know what v is, okay? It's not v of x tau, it's just v x t. So it becomes independent. So this object is actually dt. And there is a p here, sorry. So this is just dt. Okay? So I have, because there was the condition that at the end I have to reach the position x. So at the order dt, this is the last piece, and this is the rest of the path from 0 to t. Okay? So I'm considering path the starting 0, okay, all the path. So I am at time t plus dt. This is the time t. I have all, let's say that I start from 0. I end up in x. And so I'm considering all the path that at time t plus dt arrive exactly at x. And so this is the reason why I can compute the last step of the integral at the order delta t, okay? Because between t and t plus delta t, I can approximate v as the final point, delta t being very small, okay? So now what is missing is what is this? And so this is z, p, but now I'm not, so here there is t, but now is not ending in x, but is ending in x minus delta x, which is the last jump, okay? And this delta x is random, so I put it like this. This is the average over delta x, and because delta x was a free path, and this was the mean square displacement, I have the delta x average is equal to 0, and delta x square, if is delta t, the jump is of delta t, so it will be t delta capital T dt. Okay, so this is the average over the last jump. So I have a random walk. Each jump has this variance, okay? And when I have many jumps, I do the t times t mean square displacement. And then I have my term that doesn't move, which is this one. Okay, now I'm almost done. What I have to do, I have, the only thing which is random now is delta x, okay? So I have to expand this z in order of, so I will have the first term in delta x, no? The first term is just z p x t, which is deterministic, so the average is just z p x t. Then I have the first order, so is minus delta x. Then I take the derivative with respect to x of z xt. And this I have to average. And then I continue, there is a term delta x squared. And here I have a second derivative. And then I can go on, but I will stop here at the second order. And then you can do delta x cube and so on, but it will be 0 delta x cube, so there will be something delta x4. And now we can expand also this. This is 1 minus p vxt dt. Okay? So this term I developed up to the second order, and I took the average over the stochastic part. This term has no stochastic part, but again, I stop at the first order in delta t, okay? And now you can make the product between the two. We have a first term, which is the dominant one, which is zpxt. Then we have the terms which are, then we have this term, minus p vxt dt times z. Okay. Then we have this term. What is the average of delta x? 0. So this term is actually, hopefully is not there, okay? But this term is there, okay? And so this term is plus capital T over 2 dt, second derivative of z p x t. And then should I do the product with this and this? No, because it's of the order delta t squared. So I'm happy like this. And so what I have is that z p x t plus dt. This term I can put on the other side, minus z p x t is equal to dt that multiplies two terms. The first one is t by 2 second derivative of z p x t. And this term is minus p v x t z p x t. Okay, and now I have my differential equation. I have the derivative of z p x t is equal, I like to write in this way, minus, then we have minus p by 2 second derivative of x. Then we have plus p, and p was 1 over t. You remember, I did this here, so I took p equal 1 over t. So it will be plus, so yes, it was 1 over p. So let me check after, I will check if it's 1 over t or minus 1 over t. So this is of the form minus hz, okay? And this is in the imaginary time, the Schrödinger equation, okay? What is important is here you see that z multiplies both the Laplacian and the potential. It's not the diffusion equation for which you have z here, but I mean, there is no potential, like there is no multiplication with the noise. This is the Langevin equation, is where you will have z here, but not here. And this is a Langevin noise. This is not an additive noise. This is a multiplicative noise. So this is a Schrödinger equation. And this is an equation with multiplicative noise. Because V multiplies Z, okay? And so it's difficult to deal with them. And, but we have a form which is suggestive because it's the Schrödinger equation. Now the problem we have is that it's stochastic, but also that is time dependent, okay? Usually, you solve the Schrödinger equation with a time-independent potential, okay? And when the Schrödinger equation is, let me erase maybe this part which is more technical. So in the time-independent case, that is what we will do tomorrow using replica. Okay, in the time-independent case, what you usually do is that you solve, you characterize the spectrum of H. So usually you can have two kinds of eigenstate solution. You can either have what is called the bound state, which has negative, discrete negative energies, okay? If you have an attractive potential, you can have some bound state. Or you can have, so this is discrete. N is an integer number. Or you can have the continuum part of the spectrum. These are called the scattering states. Usually are there for positive energy. Are typically the plane wave when you do the free particle problem. So this E bigger than 0 is the continuum spectrum. This is when it's time independent, okay? And then for that, if you have these eigenstates, and if it's of the form dtz equal minus hz with h, which is time independent, then z of xt is of the form exponential minus th. And then you have to evaluate the elements that go from 0 to x, and then you use this spectral decomposition, okay? And essentially what you have, it is given by, so you start in 0, you arrive in x, and then you have the factor exponential minus e and t, and this is for the discrete part of the spectrum. I don't know how many they are. And then you have the continuum part of the spectrum with some density of these scattering states. And you have psi E0, psi star E in X. Exponential minus et. So this is the general form of z x T, the spectral, the decomposition on the eigenvector of the Hamiltonian. This is possible, so this time dependence becomes trivial for the eigenstates only if V is time independent, okay? So if you don't have a noise which is time dependent, then the problem becomes easier. You solve the eigenstates problem, okay? There is the bound states, the continuum part of the spectrum, and you can write the full solution for the partition function, okay? Unfortunately, our problem is not so simple, but the replica trick that I will introduce tomorrow allows to take the average. So we can compute the moments of the partition function, essentially. The replica trick is nothing but the moments. So I will compute Z average. So I will take the average on Z. I will take the average on Z square. And we will see that then we end up to a quantum problem, which is perfectly deterministic, and with a potential which is non-time dependent. And so we can reformulate the problem of the computation of the moments of the partition function as a standard quantum mechanical problem, time independent. And this allows to make progress, and this allows to find the solution of this model. So let me see how much time I have. 15 minutes, okay. So, yes? Because it was there. So is when I defined this here, if I take P equal 1 over T, I have back my model of the beginning. Okay, it's okay? Sorry, I missed to say that. So here, when I do this kind of Laplace transform, is a generating function of this one. You see that now if I take P equal 1 over T, then I go back my model of the initial model, okay? So you do all the calculation using the average over the free particle, and then at the end, you replace P with 1 over T, and then you get this Schrödinger equation, so which I erased, but actually I have to rewrite. Let me rewrite here the Schrödinger equation. So is Z xt is equal to minus, so we have a minus here, t by 2 second derivative of x, plus Vxt over t. Okay, and I always forget, but it's very important here is Zxt. Okay, this is the Schrödinger equation that we have if, so this is the Hamiltonian if you want. And so this is time dependent, and when it becomes time independent, we can solve it. So let me maybe make in 10 minutes, maybe I will, yes. And
then solve for the energy, then we only get the determinants part.
Okay, actually, this is a very good question. Actually, we cannot solve in this way because it's time dependent. But when we take the average over the disorder, okay, I understand. No, so we have first, at the first moment, we have the annealed result, which maybe is correct for some high temperature regime. We will understand together, okay? But maybe not. Then we compute the second moment, and we verify if Z square divided, so if the second moment divided the first moment square is finite or divergent. When is finite, we will say, okay, the annealed average is correct, and this is the result, and essentially you will find the physics of the free polymer. So you will find that the roughness exponent is 1/2. It's like if you pick at random one polymer. But if it's explosive, as it will be, then you are in the glassy phase, and it means that at any temperature you are attracted by the ground state, actually. So you will see only small excitation on top of the ground state, but if you are in the glassy phase, you will not explore the phase space, but you will be stuck in the ground state at all temperatures. So this is the picture will emerge. Unfortunately, if you want to extract really this prefactor, you have to solve the model at all the moments, so it's very difficult. So what people does is then are able to find expression for Z, for generating function of the moment of the partition function, and this is the way people solve analytically this model. This is very difficult, but already at the second moment is non-trivial, and you see when you have the glass transition and when you don't have the glass transition, okay? So tell me more or less, I can say what happens in the mean field. Ah, this is the time, okay, 10 minutes, okay. So let me make this, so tomorrow I will solve the moment, so I will take the average. Now there is no time for that. But let me say, today, I've mostly done the case n equal to 1. And I just told you the n equal to infinity is similar to the ramp. But actually, the n equal to infinity is a very famous model. I will not explain it, but there are a lot of people that work on that. So to define well the n equal to infinity, you define the directed polymer on a Cayley tree. So you change lattice, okay? You have a lattice like this. So this is 1, 2, 3, 4 generation. Okay, and again, the polymer, this is a typical configuration. Okay, this is another configuration. Okay, these are configuration of the directed polymer on a Cayley tree. So it's a completely different lattice, okay? There are no possibility, so you can follow, two polymer can follow up to a certain time, but then when they split forever, okay? It's not possible to come back. You cannot have things like this. It's impossible to have loops of this kind. Once you split, it's forever on the tree. And this makes a major approximation. Again, the energy is the same definition. So the energy along x of tau, it will be the sum from tau from 1 to t of v x tau. Okay, it's the same definition as before. So each energy is a random number 0t, okay? But compared to the RAM, it's not as simple as the RAM, because if you draw two configurations with a big overlap, I need another color, I use the yellow, the blue. If you draw a configuration, two configurations with a big overlap, they will have similar energy. Okay, the blue and the orange will have a very similar energy, while the orange and the yellow will have different energies because they are completely different paths. Okay, so there is something more in this model, but actually there is a famous solution by Derrida-Spohn of this model, and this model essentially shows the same freezing transition. So the point 1 is exactly the same. The free energy is like this and become like this exactly at the same temperature. There is a difference. So because of the Cayley tree structure, here is 3/2. It's not 1/2, okay? And chi is not Gumbel, but it will be a different distribution that depends on some feature, okay? So it's not known exactly. So there are features that arise from the fact that this is an interacting model, is a model with interaction between configuration. But on a qualitative point of view, is very similar to the RAM. It displays a freezing transition, and the fluctuation of the ground state energy are of the order 1. So when you find the ground state, the other states close to the ground state have a fluctuations of the order 1. So the first excited states will be at the same energy plus 1, or something of the order 1. While for the directed polymer in 1 dimension, 1 plus 1 dimension, it's very different. To move a piece X from the ground state, it will cost you X power theta. So it costs a lot to make an excitation different from the ground state, while here you can have essentially excitation. So you can have either, so in this one-step replica symmetry baking, what happens is that when you look at the state close to the ground state, so here you have your ground state, and then you have few states with small L energy, okay, with an energy cost, let's say 10. And then you look at them, which kind of polymer I will find. Okay, and you can show rigorously that there are two possibilities. Either you have a small modification, so let's say that the orange one is the ground state, okay? So either you will do like the blue, so this is a possibility, so you will be exactly like the ground state, but at the last minute we will do something else. This has a cost of order 1, but the surprising fact is that you can have also small energy excitation, like the yellow one, so that from the beginning they took another path. They are completely different, geometrically completely different, but they have an energy which is very similar, okay? And so this is called one-step replica symmetry breaking, because the low energy states, either they are very similar, so their overlap is almost 1, either they are very different, so the overlap is almost 0. Okay, so there is no intermediate. So you cannot, there will be no something that up to the half follow the ground state and then change their mind. Okay, either you change your mind immediately and you have a solution which is low energy, either you change the idea at the last minute, and this is just a small modification of the ground state, okay? So this is a feature that you don't have in the 1 dimension. In the 1 dimension, you have only the ground state, and the only excited states that you see close to the ground state are very similar to the ground state. And I think this is a good point to stop. I didn't show that, okay? But I just say that this model has these two features in the two extremes. In the large N limit, it's similar to the RAM, and this feature that at low energy you have many states which are very different. And the directed polymer in 1 dimension, we will see tomorrow, it has only states which are very similar to the ground state, and it has no many states which are very different. Okay, so that's it. Yes? Yes. So what the elastic term does is that you, so what if there was no elastic term, what you will do is try to pick the most extreme value of V. So let's say at each time step, you will try to pick the smallest V, even if it's very far. So you will have a polymer that do something like this, okay? It will be very, very rough, okay? So the elastic curve punished that and say, okay, you can find the best V, but you pay an elastic cost. So the more bigger is the elongation, the more it costs energetical. So you have to find a compromise, and this is what makes the problem interesting, because you have to optimize between the elasticity and the disorder. And the optimization is what gives you this exponent 2/3 for the roughness, 1/3 for the energy. Okay.